So now that's the end of the lectures today, as it were, except, of course, Chris is now going to explain to us all why Wei Zhang is this year's recipient of the Clay Research Award. Where is Wei? I'm getting slightly nervous, I haven't seen him. Oh, Wei, hi. Why don't you come sit down the front, Wei? Yeah, you can be maximally embarrassed if you're sitting in the front row. Okay.
Well, I'd like to start by thanking, of course, the Clay family, the Clay Foundation, and the Clay Math Institute for their support of this conference and mathematical research in general, and also the scientific committee of the Clay Math Institute for giving me the opportunity to speak briefly about some beautiful mathematics. So I'm going to talk a bit about the mathematical work of Wei Zhang. That's actually an impossible task. So, but I'm going to talk about a little bit of it. And I'm not even going to so much talk about exactly what he's done as explain why it's interesting to someone like me, who is a mere number theorist. But before I do that, I'd like to give a little bit of a brief introduction to who Wei is. He's got his bachelor's degree in 2004 from Peking University. And I bring that up because he was actually one of a number, I don't know what they were teaching that year, but he's one of a number of stellar mathematicians who graduated that year who have made a huge impact on this field and these problems that Gan Gross mentioned. He went on to receive his PhD in 2009 from Columbia University under the Shou Zhang as his advisor, held postdocs at Harvard, including a Benjamin Pierce Fellow. Returned to Columbia as a professor until 2017, and since 2017 he's been a professor at MIT. In 2010 he won the Sastra Ramanujan Prize, and in 2018 he was a recipient of the New Horizon Prize, which he shared. He's a fellow of the American Math Society, but that's just a CV. So who's Wei? Wei is a mathematician and one with an infectious enthusiasm for mathematics. So I think you can see that, both that enthusiasm and his generosity in the lectures that have taken place in the workshop that we're running on the Gan Gross Prasad conjectures and new advances. Many of the speakers are people who have collaborated with Shou Zhang or been inspired by the mathematics. Collaborated both with Shou Zhang and Wei Zhang, and have been inspired by the mathematics of Wei Zhang. And I'll even say a little bit about that as we go on today. All right, so the mathematical contributions of Wei. These include a proof of the global Gan Gross Prasad conjecture for unitary groups via the relative trace formula that was alluded to in Dick's talk. An arithmetic relative trace formula approach to the arithmetic Gan Gross Prasad conjecture for unitary Schmor varieties, and also some results that go beyond the Gross-Zagier formula, at least for function fields. So I'm going to try to say something about all of these, and I'm going to talk about them as a number theorist. So to me, these are all about L functions and special values of L functions. So so what are L functions? So one way to think about L functions is that they organize data at the primes. Prototypical example, the Riemann zeta function, which organizes the primes in such a way that reflects the unique factorization of integers. Another example of interest to number theorists is if you have an elliptic curve over Q, there's its Hasse L function, and it's organizing data related to the number of points on the elliptic curve over a finite field. Okay. But as was also mentioned in the previous talk, L functions have an analytic origin often. They are transforms of automorphic forms. At least we hope so. That's part of the Langlands program. And as such, that gives us the source of many of their nice properties: analytic continuation, functional equations. This goes back to work of Riemann. We have this famous Riemann integral where he expresses the Riemann zeta function in terms of an integral or a Mellin transform of the theta function. So here we have an L function as a transformation of the basic example of a modular form. And by rewriting this in suitable form, you get you can see the functional equation of the Riemann zeta function following up. So this was essentially Riemann's one paper on number theory, and it's been extremely influential. So elliptic curves. After a lot of work, we know that exactly the same thing happens. The L function of the elliptic curve, which I wrote down as an Euler product having to do with points on the elliptic curve over finite fields, is actually the Mellin transform of some modular form. And by a similar sort of manipulation of this integral, you obtain a functional equation. And functional equation at the moment goes from s to 2 minus s. So s equals 1 is obviously an interesting point. And then there's this sign plus or minus 1 that showed up as an epsilon factor in the previous talk. And here I'm using the notation w, which is sort of historical, and also I will refer to it as a root number. All right, so these are L functions. Okay, so why is this sort of split personality of L functions interesting? Because somewhere, as a consequence of all this, one gets global number theory involved. And what it is that special L values, so values of the L functions at certain special points, actually seem to have interesting arithmetic about the integers, not just about things at primes, and not necessarily about just things of analytic origin. So here's an example. Zeta at a negative odd integer is a non-zero rational number. In this case, zeta of minus 11 is 691 divided by 32,760. 691 is a prime, and the fact that it appears in this numerator actually tells us that 691 divides the order of the class group of a particular number field, the number field where you join the 691th roots of unity. So there's arithmetic encoded in these rational numbers. We expect similar things for special values of the L functions of an elliptic curve, the most interesting perhaps being the Birch-Swinnerton-Dyer conjecture, where we expect that the order of vanishing of the L function at the center of that critical strip, which was s equals 1, is the rank of the Mordell-Weil group, this is a finite group of rational points, finally generated abelian group. In particular, if the sign of that functional equation, that root number, is minus 1, the L function vanishes at s equals 1, because you have whatever the value is equals minus 1 times itself. And then this conjecture would tell us that we would expect the rank of the Mordell-Weil group to be at least positive. Okay, so that brings me to the global Gan Gross Prasad conjecture. Believe it or not, I'm going to bring it right back to elliptic curves. So we have two unitary groups, one on a space of dimension n plus 1 and one on a space of dimension n. We take their product, and we'll call that G. And then we look at the smaller dimensional unitary group on the smaller dimensional space as a diagonally embedded subgroup. And then this is, I'm just restating the global Gan Gross Prasad conjecture from the previous slide, previous talk. But if we take some cuspidal automorphic representation of the delic points of this larger group G, so that's just a collection of particularly nice functions, or a space of particularly nice functions on this group that transform stably under the action of the group itself. And we can look at what we call a period integral, which is just an integral of an element of the space over the points of the subgroup H. Actually, if you go back to the Riemann zeta function, this is in fact can be reinterpreted as integrating a function on GL2 over a diagonally embedded GL1. All right, so these kinds of formulas aren't totally new. Anyway, so the consequence of Wei's results towards the global Gan Gross Prasad conjecture is that this integral or collection of integrals is not identically zero if and only if that the space of homomorphisms from the representation pi to C that are H invariant is not zero. That's obviously sort of a necessary condition. It's not quite sufficient. We also have this sort of global arithmetic entering that the L function doesn't vanish at a half. And I've stated this way so I can avoid any reference to the local conjectures that took up sort of 75% of the last talk. All right, but as I want to just talk about why is this interesting? I mean, that's a fantastic piece of work, but I have to convince you that this is a fantastic piece of work. So why is this of interest to number theorists? So we're talking about these period integrals. Well, so these period integrals often have geometric or combinatorial interpretations. So the point is, once we have such a formula, just like the Langlands correspondence not being an end of the story, such a formula or such a statement connecting non-vanishing of periods to non-vanishing L functions is not the end of a story, but just the beginning. And so now we can use geometry to study L values and vice versa. So going back to elliptic curves, so if you look at the L function of an elliptic curve, and you can twist it by one of these Hecke characters that also appeared in the previous talk, it turns out to be an L function for one of these representations in the case where n is equal to 1 and n plus 1 is 2. So on u2 cross u1. And then in these cases, the period integrals can often be interpreted geometrically as summing some function or some differential and its values on some special points on a curve or even on some combinatorial gadget. And so then you can start to do things because you can use distribution results for these special points. Maybe they become equidistributed on the curve. And then you can sort of say at least one of these characters, the L function, is not going to vanish because one of these period integrals, not all the period integrals can vanish, or the function that we were evaluating at these points would just be identically 0 on the curve. And in fact, using results like that, people were able to prove non-vanishing results for large classes of characters in contexts that seem to be beyond the reach of traditional methods from analytic number theory. And then one can also go backwards, because if you remember, the GGP statement is an if and only if. So if you knew that the L function is vanishing or doesn't vanish, then that gives you some information about special points. So that's one reason that number theorists get interested by results like this. And so having the global Gan Gross Prasad conjecture now, we have a much wider context in which we can study similar problems. All right, so another place where this period, or something like these period integrals enter, is in the generalizations of the Gross-Zagier formula. We have an imaginary quadratic field. So the previous thing that I talked about, the non-vanishing of the L value, well, if it doesn't vanish, the sign of that functional equation or that root number has to be +1. So what about the -1 situation? So these period integrals are all 0. What can we do? Well, so then I'm just going to very briefly recall there was a beautiful formula but by Gross and Zagier that related the derivative of the L function then, in this case, at the value 1, at that central value, to the height of some special point related to the imaginary quadratic field. Okay. And then, as was sort of also alluded in the previous talk, then some work of Kolyvagin allowed us to take that point and conclude that the rank of the elliptic curve is actually 1. All right. So we'd like to do something more generally. Anyway, so the kicker here was that the order of the L function being exactly 1 meant that the rank of the elliptic curve, the Mordell-Bay group of the elliptic curve in this context is also 1. And now we'd like to do that in greater generality. Actually, we'd like to handle the case where the order of vanishing is greater than 1, but that's a hard problem. So the arithmetic Gross, or Gan Gross Prasad, is a generalization, at least a conjectural generalization of the Gross-Zagier formula. So you start with these two groups, and all I've done is change the way I've written the groups to emphasize the signature at the Archimedean place, or as real groups. That gives rise to, each of them in this context gives rise to an algebraic variety. The embedding of the groups gives an embedding of algebraic varieties. This gives this cycle. The codimension here is n, so it's in the Chow group cycles of codimension n. I'm going to pretend that they're homologous to 0. Okay, so this is all about making precise statements, which seems kind of beyond, not the point of this lecture. So the idea is then to replace the automorphic period integral with an arithmetic period. In this case, it's just the intersection of these cycles. or two of these cycles. So we have the cycle that's generalizing our Heegner point, and then we intersect with cycles in some representation space. And there's an analogous conjecture to the Gross-Zagier, which is that this intersection number, or at least one of them, is non-zero if and only if the L function doesn't vanish, and then there's some sort of representation theory condition. All right. In this context, Wei has actually supplied us with a strategy that may actually prove this. And not only that, it gives a new proof of the Gross-Zagier formula, or at least sets that proof in a context that seems much wider. What about, I also mentioned that he's gone beyond Gross-Zagier. So both the global Gan Gross Prasad and the arithmetic Gan Gross Prasad are only telling us information about the first two coefficients in the Taylor series expansion around the central critical value, which I'm writing here is a half, but for elliptic curves it would be 1. And so what Wei and his collaborator Ji-Wei Yun have done is prove that if pi, not if it comes from an elliptic curve, say, over Q, but if it becomes, say, for an elliptic curve over a function field. So function fields of curves over finite fields are often the testing ground for conjectures over number fields. They behave the same. Those are the two classes of global fields. And and sometimes there's more geometry to exploit for the function field. And so in this case, they proved an absolutely beautiful formula for all, well, I should say, depending on the parity of R, for all, in this case, I guess, all even values of R, they prove a beautiful formula for that Taylor series coefficient as the intersection of some cycle, or actually self-intersection as I've written it, of some cycle on some very large moduli stack of Stuckos. So some vast generalization of modular curves in this context. All right. So that's quite intriguing. We still have no idea what the analog of this might be for number fields, and so, but it's always good to see what's happening in the function field case as a way of sort of trying to guess what might be true for number fields. You can also, this is also kind of interesting stuff because if you can mix it all together, and the question was raised in the first talk, how do you go from the elliptic curve having rank 1 to the L function vanishing to exact order 1? Well, here's one way, though it assumes something that our previous speaker didn't want to assume. So the way we get a handle on the elliptic curves of the Mordell-Weil group is often by taking this finally generated abelian group, reducing it mod p, that gives us a finite group over fp, seeing it inside some other vector space over fp, but that has a sort of slightly more tractable definition called the Selmer group. And suppose our Mordell-Weil group had rank 1, so this would be fp, and suppose also the Selmer group is fp. We would like to say, so that'd be fine. But suppose we only know that the Selmer group is fp. We'd like to actually conclude somehow that the Mordell-Weil group has rank 1, and this is actually expected consequence of the finiteness of the Tate-Shaffer-Average group, but maybe we could actually prove it. So what happens is that you make some nice choices. You pick some primes in the number field where things, the Selmer group gives you a restriction to the local points, and maybe that's still capturing everything since it's a one-dimensional vector space. And then there's a sort of a way of describing all of these points as the surjective image of points that come from a unitary group. This is an old result of Ihara. And so then if you follow this arrow, you go this way, this way. This is actually, well, it's some function, but it's actually one of those period integrals in disguise. Well, it's one of the functions that you would test on a period integral. And so there's also, remember, there's a candidate for what this point should be. It was the Heegner point. And so the value of this point of the Heegner point over in Z mod pz is just the value of one of these period integrals mod p. And if you were very clever with your choice of L and some other arithmetic information that you have, you could have chosen L such that this period integral was non-zero mod p, and that would mean that this cycle, or this Heegner point, had to have non-zero image here, because some function evaluated on it is non-zero. And so that means it's a point, well, under reasonable conditions, that means it's a point of infinite order. Fine, what does that gain you? Well, what that gains you is that you can do some stuff with it. And so one of the other things that Wei has done is taken those ideas that I sort of rapidly went through and given a proof of a conjecture of Kolyvagin about the structure of Selmer groups of elliptic curves. So we now know in many cases how to completely describe the Selmer group and the Tate-Shafter-Ravitch group of an elliptic curve in terms of cycles or classes coming from cycles. And also, these ideas led to a proof that the majority of elliptic curves satisfy that the rank is equal to the rank of the Mordell-Weil group is equal to the order of vanishing and is either 0 or 1. There's a natural way of counting elliptic curves, just in terms of the coefficients of the equations. And the expectation is that 100% of the curves have ranks 0 or 1. And we can now know that at least a majority of them satisfy that condition. All right. Back quickly to global Gan Gross Prasad. I mean, hopefully I have at least intimidated you into believing that number theorists find these results interesting. But what has Wei really done? So now I'm going to try to convince you that it's actually some beautiful, deep mathematics. So we're trying to prove, remember, that some period integral is non-zero if and only if some L value is not zero. So how are you going to prove something like that? What you would like, maybe, is a formula for this L function exactly in terms of these period integrals, and then you'd be done. And that certainly holds, for example, in the Mellin transform of the modular form associated to an elliptic curve, but these periods are a little more mysterious. So what Wei did was realize an idea of Jacques and his school, which is to take a trace formula approach to this. So in the trace formula, you look at sort of compactly summated smooth functions on your group. You average you form a kernel by summing over all elements of the group, and then we're going to perform a distribution by integrating this kernel over, which is a two-variable kernel, over the group H, the subgroup H in each of these variables. And then in the trace formula, there's always a spectral side and a geometric side. The spectral side decomposes with respect to, say, eigenvectors, if you will, for the action of the convolution action of these functions. And so you get a sum over some nice functions of products of period integrals. So the period integrals show up in the spectral side of the trace formula. And then there's a geometric side, which you just expand with this function, and you end up a sum over actually a subset of gammas of orbital integrals, which are just nice sort of local integrals. So, so we're interested in what's happening on the spectral side, and maybe we could say something by studying these orbital integrals. I should say that you can choose this f so that you pick out a function phi that's just in the one representation that you're interested in. So you can simplify many of these terms. Okay, so we can see the periods in this, but where are the L values? So L values actually show up. You do the same thing for a different collection of groups. I'm not going to go through the slide. All I wanted to say is that when you do it for GLN plus 1 cross GLN, you get period integrals. Actually, you get two period integrals. One of them actually does see the non-vanishing of the L function, because it really is, by work of Jacques, Piatetsky, Shapiro, and Shalaika, it really is giving us an integral representation for the Rankin-Selberg L function. this L function. And the other one detects those representations of GLN plus 1 cross GLN that are the image of Langland's base change from the unitary group. So the non-vanishing of this period should be saying that we can, or that if we have a small pi that we're interested in, we ought to be able to make this integral non-zero. And if the L function doesn't vanish, we can make this integral not zero. But how are we going to connect that to the periods that we had before? And the idea is the simple idea is to just say that the geometric sides of both of these trace formulas are the same. And how are you going to prove that? You're going to do it by proving piece by piece that the individual orbital integrals are the same. And that's what Wei did. And actually what happens is that the orbital integrals factor into local orbital integrals, and you have to figure out how, if you're going to equate these things, then you have to have some matching between what's indexing the integrals and what the functions that they're evaluated on. And that there should be such a correspondence had been conjectured by Jacquet and Rallis, but this was proved by Wei. So this is a great achievement. The ideas underlying this achievement have gone far beyond just proving this already remarkable result. And in fact, earlier this week, we heard a lecture from Raphael Zoplessi, who showed that some of these ideas of Wei can be used to give a very sort of conceptual proof of the fundamental lemma which underlies this relative trace formula. And now I understand, without ever having to go to geometry and come back via logic. And now I also understand that fundamental lemma implies the endoscopic fundamental lemma of Lemon and Ngo without, again, so we no longer have to go through a proof using the geometric setting and come back via sort of logic. All right, so how are we going to prove the arithmetic GGP? We're just going to do the same thing. And all we're going to do is we're going to put in a parameter s and then differentiate. And so we'll get so we put that in our second relative trace formula, we differentiate, and then the derivative of this period is going to see the derivative of the Rankin-Selberg L function. And we'll get derivatives of orbital integrals. And on the other side, we replace our period integrals in the unitary groups with the sort of period integrals on the Shimura varieties coming from intersection theory. And now you want to equate these two distributions. And how's this going to happen? Well, this height pairing, it turns out, is a sum of local height pairings. And so the orbital integrals, which were first sums of orbital integrals, but now that we've taken derivatives, they become, or they're first products, but now that we've taken derivatives, they become sums. So we have, on the orbital sort of integral side, we have a sum of orbital integrals. On the height pairing side, there's a local heights. And so now you would want to prove that these two quantities are the same. And but then you have to formulate again the precise matching of everything, and that's exactly what Wei did. He defined the arithmetic fundamental lemma, and along with his collaborators, the matching or transfers of functions on each side. And quite remarkably, this summer proved the arithmetic fundamental lemma, at least under some, at least for QP. And so, right, so that's where we are. So when I was a graduate student, I arrived at Princeton at the height of sort of the excitement about the modularity of elliptic curves, and that, as Dick alluded to, meant that we could prove lots of results towards Bert Swinnerton Dyer using the Gross-Zagier formula and stuff like this. So all number theorists, as young number theorists, we were trying to understand GL2. And thanks to the work of Part 2 of Wei, we can save some ink and some chalk by just writing G. Thanks.